Welcome back again to Advanced Functions, MHF4U 1. This is our first chapter called Exponential and Logarithmic Functions. In this lesson number 1, we're going to explore the logarithmic functions by investigating the inverse of exponential function. First, let's define what exponential function is. So exponential function is defined by y is equal to bx. So as you can see, b is the base, and x is the argument, and y is the value of the exponential function. In other words, the output. So keep in mind, for each value of the base b, you're going to get a different function, which is a different exponential function is defined. So for example, y is equal to 2 to x, and y is equal to 3x, compared to y is equal to 1 over 2x, and y is equal to 1 over 3x. So as you can see, all of this have a different base, meaning they're all different exponential function. Now, another rule to keep in mind is that when a, or the base, in this case let's do base, if base is greater than 1, that means it's going to be an exponential growth. So it will look something like this. Okay. So the higher the base, the more stretched, more exponential growth accelerated graph is going to look. But on the other hand, if I were to flip it, so if the base is in between 0 and 1, that means it's going to be exponential decay. So in other words, it's going to look like this. Same thing, smaller the base, the faster deceleration is going to be. Now, let's go over the transformation. So this is the standard transformation equation, which I wrote it in A as the vertical stretch or compression, B as in horizontal stretch or compression, C is the horizontal or horizontal left or right, and D is the vertical left or right. And keep in mind the horizontal asymptote from the exponential equation is D. Okay. Now, so if I want to write it in different method, it's same thing. So let's say f at x is equal to a b k x minus d plus c. So I'm just using different letter so you can be familiar with writing down characteristics. So as you can see, b is going to be my base. So that's my the base that defines what exponential function it's going to be. So we do have a horizontal asymptote at y is equal to c in this case. Okay. And then a is the vertical stretch or vertical compression, right? So stretch if a is greater than 1, and it's a vertical compression if it's in between 0 and 1. K, on the other hand, it's a horizontal stretch or horizontal compression. But I'm going to write a bracket. You gotta switch it. So switch, meaning you gotta flip. So therefore, if after I flip K, if K is greater than 1, it's a horizontal stretch. But if it's in between 0 and 1, then it's a horizontal compression after you flip it. Now, on the other hand, D is the horizontal translation. So it's a horizontal going left or right. Again, because it's in the bracket, you gotta think the opposite. You gotta do the opposite sign. So if I take this negative d out of the bracket, it becomes positive d. So if it's positive, it's going to the right. If it's negative, it's going to the left. And then same thing for C, it's a vertical up or down. For this one, you read it as it is. It's up if it's positive number, it's going down if it's negative number. But for this one, I'm just going to write opposite in bracket. So anything that is in the exponential form, exponent form, K and D, you gotta either flip it or do the opposite sign. Now let's do a practice example. So graph the exponential function. So as you can see, first thing is identify what my parent function is. So my parent function here is y is equal to 3 to the x because we have a base of 3. But keep in mind, I have an expression in the exponent and I have negative. So make sure you want to factor as much as possible for anything that is in the exponent. So y is equal to negative 3. Let's factor negative. So nothing's in front of x. X minus 1 plus 9. Okay. So to do all the transformation, first thing is make a graph of y is equal to 3x. So y is equal to 3x, if I may, x, y. So some of the key points, 3 key points that I would like to carry with me will be negative 2, 0, and 2. So I'm going to plug in negative 2 into x, and that will give me about 0.11. If I plug in 0 into x, it gives me 1. 2 into x, it gives me 9. And rather than doing individual transformation, let's do everything using a mapping rule. So the mapping rule is, it looks like this. So x, y, it turns it into 1 over k x plus t, ay plus c from my previous equation. So let's do the x value, which is in the exponent. So I have negative x, and then it's negative 1 here, so when you take it out, it becomes positive 1. For y, I have negative a, so negative y. Now keep in mind a is not 3. 3 is the base. So if I want to figure out what a is, then just look what is in front of the base number, which is negative 1. So negative y plus 9. So that will be my mapping rule. So what I'm going to do is I'm going to plug in negative 2 into x and 0.11 into y. So plug in all the values. And then I will get 3, 1, negative 2, negative 1. So this will be, negative 9 plus 9 is 0. And then negative 1 plus 9 is 8. So it's going to be 8.99. Okay, so let's see. First thing first, let's label our horizontal asymptote. So horizontal asymptote is at 9. So let me draw horizontal asymptote at 9. So I'm going to label y is equal to 9. So this is a line that the graph will never ever cross. Okay, and then let's label at 1, it's going to be 8. At 3, it's going to be 8.99, so it's very, very close. And then negative 1, it's going to be 0. And the graph looks something like this. Make sure you draw the arrows at both ends. Okay, and just by looking at it, you will notice that there's two negatives. So that means from my original function, it has been reflected twice through the x-axis and y-axis. It moved to the right one step and it moved up 9 steps, 9 units. If I want to compare to my parent function, it will be 2 to the 9 and negative 2 is 0.1. And it looks something like this. Okay, and for any standard exponential function, we have a horizontal asymptote of y is equal to 0 because there's nothing plus or minus 0, right? So therefore, it looks like that. So the red one is my standard, the parent function, and the blue one is my transformed graph. Now, let's explore the difference between exponent and logarithm. Now, so we understand that, so for example, in an exponent form, 2 to the 3, 3 is the exponent and 2 is the base. So what this really means is that it's 2 times 2 times 2 is equal to 8. So a logarithm goes the other way. It asks the question, what exponent produces this? So what it means is that 2 to something, 8. So what exponent produces this? So a logarithm is therefore the exponent that must be applied to the base to get the x value, okay, which is the question mark. So if I want to translate this, so for example, I have 2 to the 3 is equal to 8. So this is my exponent form. And if I have to change it into logarithmic form, it's going to be log. The base stays the same. So the base is 2, but in subscript. And the 8 goes right beside the logarithm and is equal to 3. So 2 and 2 is the base, and it's also the base of the logarithm, and the exponent switches place over here. That's the exponent. Okay. So as you can see, exponents and logarithm undo each other. It's inverse as long as the base is the same. Okay. So therefore, for example, if I were to have exponent of, let's say, 4 squared is equal to 16. So if I want to put it in a logarithmic form, it's logarithm, log to the base of 4 to 16 is equal to 2. So easier way to see it is 4 to the exponent of 2 is going to give me 16. So that is the relationship between exponent and logarithm. So a logarithmic function is defined as the inverse of the exponential function. So inverse meaning that they're going to be symmetrical through y is equal to x. So what that means is that all you need to do is switch x and y to go from one to another. So if we're given y is equal to bx, then x is equal to f inverse of y. Okay. Note that b is the base of the exponential function and the base of the logarithmic function. So the base stays the same. So this is the interchange relationship between the exponent form and logarithmic form. And we read it as log to the base of b of y, or b to y. Okay, so they mean the same thing. So make sure you memorize this format. So let's do a quick example. So convert each exponential form. So we're given logarithmic form, and let's turn it into exponential. So the base is 2. 2 to 4 is equal to 16. Now, as you can see for letter B, there's no base here. If the base is not written, then assume that there's invisible 10. That is the standard logarithmic with a base of 10. So it's going to be 10 to the exponent of negative 4 is going to give me 0.001. Okay. Next, let's convert exponential form into logarithmic form. So first, identify what the base is. The base is 3. So logarithm has a base of 3 of y is equal to 5. So double check. 3 to the 5 is y. Next, in this case, the base of 3 again. So log to the base of 3 of 27 is equal to x. Let's double check. 3 to exponent of x is 27. Now this time we're going to solve for x. When you're solving, you never try to solve it in logarithmic form. Always turn it into exponential form. So let's change it into exponential form. 3 to the 4 is equal to x. Then punch it in your calculator. X is equal to 81. Okay, simple. Always change it into exponential form. Next, 2 to the 5 is equal to 4x. 2 to the 5 is 32 equals 4x. Let's divide both sides by 4. X is equal to 8. Now, this time, we're going to take a look at the graphs of a logarithmic function. From the previous slides, we understood that logarithmic functions are the inverse of exponential function. So what does inverse mean? They are reflective through y is equal to x, which is a straight line. And the domain and range, all they need to do is switch, and x and y value needs to be switched as well. Okay, so for example, so before we do an example, let's go over domain and range. Now, the domain for exponential looks like this. Now, so domain for the exponential function is that x can be any real number, right? So negative infinity to positive infinity. But for range, it has to be greater than 0 because we have a horizontal asymptote at y is equal to 0. So 0, positive infinity. So domain and range for logarithmic function is all you need to do is switch it. So the domain for logarithmic becomes the range of exponential, and range for logarithmic becomes it's from the domain of exponential. Now keep in mind that base always has to be greater than 0, but it cannot be 1. Why? Because if it's a base of 1, anything to a base of 1 is just going to be 1. Therefore, it's not going to be exponential, it's going to turn it into linear function. Let's do a practice now. So sketch the following graphs and state the domain and range. First, I'm going to draw the table of values. for y is equal to 2 to the x. So let's pick some points. So negative 1, 0, 1, 2. So I'm going to plug in negative 1 into x. I get 0.5, 1, 2, and 4. Now for logarithmic, what I'm going to do is I'm going to do an inverse. So what that means is x now becomes y and y becomes x. So let's switch them. It's going to be 0.5, negative 1, 1, 0, 2, 1, and 4, 2. Now domain for exponential, it's going to be x can be any real number. And for range, we'd said that y can be any real number such that y has to be greater than 0. Well, what does that mean? They're going to switch now. So domain, let's do this way. So domain is now x can be any real number such that x is greater than 0. And range is y can be any real number. So I'm going to plot my exponential function in blue color. Let's plot the points. So this is my exponential. Okay, y is equal to 2 to the x. I'm going to graph the logarithmic function. So let's switch the points. So 0.5 is negative 1. 1 is 0, 2, 1, and 4, 2. And the graph looks like this. So as you can see, if I have to draw invisible y is equal to x, they are perfectly symmetrical, right? They are a reflection of each other. And double check the domain. X can be any real number, but y has to be greater than 0 because we have a horizontal asymptote. Y is equal to 0, right? But on the other hand, logarithmic function over here, it doesn't have a horizontal asymptote. Instead, it has a vertical asymptote of x is equal to 0. So again, the asymptote has to switch as well. Next, so we have a different base now. So it looks like it's 1 over 2, which is going to be exponential decay. Same thing, I'm going to make a table of values, x, y, negative 1, 0, 1, 2. Let's plug in negative 1 into x. It's 2, 1, 0.5, 0.25. Now logarithm, same thing as a base of 1 over 2. I'm going to inverse this, switch the points to negative 1, 1, 0, 0.51, 0.25, and 2. Domain and range. X can be any real number. Range. Y can be any real number such that y is greater than 0. Same thing. Now we're going to switch. Domain for logarithmic is y can be any real number such that x is greater than 0. And range is y can be any real number. I forgot to switch the sign. So this is x. Okay. Another thing, so for exponential, we have a horizontal asymptote and y is equal to 0. But on the other hand, for logarithm, we're going to have a vertical asymptote at x is equal to 0. It's the same number. So let me draw the exponential in blue color. So negative 1, 2, 0, 1, 1, 0.5, and this. So it looks something like this. Okay, so that is my exponential. Let me draw the logarithmic in the red color pen. So 2, negative 1, 1, 0, 0.51, 2. Okay, so as you can see, it looks something like this. Okay. Now, so how are they symmetrical? So let's draw the straight line again. They are symmetrical. Why? Because this component, this line, is now here. And this component is now symmetrical through this part. Okay, so for exponential function decay, if I were to switch it to logarithmic, they actually overlap. Okay. So let's do a quick summary. So from what we learned so far, we understand that if it's exponential growth, meaning that the base is greater than 1, it's going to look like this. Okay. But for logarithmic, that is inverse of this one, it's going to look something like this. Okay, so keep in mind vertical asymptote at x equals 0, horizontal asymptote for y equals 0. Why? Because they're symmetrical through a straight line. And this is the only case if base is greater than 1. So exponential function, it's increasing, and the logarithmic function is also increasing as you read left to right. On the other hand, if I have exponential decay, decay happens when base is in between 0 and 1. Keep in mind, the base cannot be 1. So decay will look something like this. For exponential, okay, again, we do have a horizontal asymptote at y is equal to 0 for exponential. But on the other hand, the logarithmic function, it will look something like this. Okay, so this is logarithmic function where vertical asymptote at x is equal to 0. And again, they are symmetrical through a straight line. For exponential function, it's decreasing function. And as you can see for logarithmic function, it's also decreasing as well.